Hi guys, my name is Mohammad Izhaan Khan. Currently, I'm pursuing my bachelor's degree in civil and environmental engineering from IIT Patna. So today we begin our topic. Discussion is on communication system. So three waves A, B, and C of frequencies 1600 kilohertz. A has a frequency of 1600. B has a frequency of 5 megahertz, or like 5000 kilohertz for B. C has a frequency of 60 megahertz, 60,000 kilohertz, respectively. These are to be transmitted from one place to another. Then, which of the following is the most appropriate mode of communication? All right. A is transmitted by space, while B and C are transmitted via skywave. All right. A is transmitted via ground, B via sky, C via space. B and C via ground. All right. All right. There are like some options have been given. So the key concept behind this question is that the radio waves emitted from a transmitter antenna, it can reach the receiver antenna by the by some modes of operation, which I'll write over here. So number one is ground wave propagation. Okay, this is number one, and the frequency range which the ground wave propagation follows is 500 kilohertz to 1710 kilohertz. Number second is the sky wave propagation. Sky wave propagation. Okay, so it follows the 2 megahertz to 40 megahertz criteria. The frequency ranges between 500 to 1710. These can be transmitted by the ground wave. The sky wave will be used in transmitting the 2 megahertz to 40 megahertz frequency signals. And lastly, we have the space wave, which will carry the largest frequency modes. So space wave propagation. Okay, so it is going to give you a 54 megahertz to how much? 42 gigahertz. All right. Now let's check. So A will be transmitted by ground wave propagation. Okay, ठीक है. तो A via space wrong. A via ground. A, B and C via ground. B is transmitted via ground. A, C. So correct option is B. And let's see for more. So B is in the range of 5000. Okay, so it can be written as 5 megahertz, 5 megahertz. So obviously you can see that it will be propagated through the skywave propagation method. So A via ground, B via sky, and similarly space wave will carry the. Moving on to the next question. Next question up we have question number 2. A 100-meter long antenna is mounted on a 500-meter tall building. All right, then the complex can become a transmission tower for waves with lambda. So basically, there's a relation between the length of the tower, the height of the tower, and the lambda which it can propagate. So I'll show you. Basically, what happens is the total length of the antenna should at least be equal to lambda by 4. This is what the theory is, and this is what you have to use for questions like this when they don't give you the minimum or maximum terms in these questions, but basically the idea is the same, that the length should be minimum lambda by 4, and then you just equate it. So if we see the length of the building, L of building has been given to us as 500 meters. All right, length of antenna has been given to us as 100 meters. All right. Now we know wavelength of the wave. This antenna is responsible for the transmission of signals. So this length will be responsible for the transmission of this wavelength lambda. All right. This is logical enough because no matter how high the building is, if your antenna will be small, it will propagate small wavelength signals. So the length of antenna, here I'll write it. Length of antenna. So there's a scope of mistake over here. You can add these both two terms, LA plus LB is 600 meter, and then equate it. That will be wrong. And I told you now why will it be wrong. Suppose that there's a mountain. Okay, mountain of like 500 meters high, and there you install a small antenna of only 100 meter. Meanwhile, on ground there is an antenna of 200 meters. 200-meter long antenna is there. No, it has a range. All right, it will carry a higher lambda than this. Why? Because the antenna is small. Na? It is situated at a height, but actually the antenna is small. All right, so simple concept. Don't get confused between this. Okay, so solving it now. So the wave which can be transmitted can be written as length of antenna equal to lambda by 4. All right, so I'll write it. Lambda can be equal to 4L, which is equals to 4 times 100, which is equals to 400 meters. So lambda is nearly equal to, always write nearly. All right, nearly equal to 400 meters. Now, checking the option. See, nearly option. I told you, na, it is nearly equal to 400 meters because you L equal to lambda by 4. Meanwhile, L is always greater than or equal to lambda by 4. It is said like that. So you are taking an, so then you have to put this tending value. It is tending. It is not exactly 400 meter. This is what you should know. It can be 405. It can be 410 or maybe something like that. But it will not be 400 exactly. So moving forward. Next up is question number 3. Okay. So a 1 kilowatt signal is transmitted using a communication channel which provides attenuation at the rate of 2 decibel per kilometer. All right. If the communication channel has a total length of 5 kilometers, the power of the signal received is, and the gain in decibel has been given to you, it is 10 log P naught divided by Pt. If I want to write the power of the signal transmitted, power of signal transmitted Pi, it has been given to us as 1 kilowatt. All right, 1 kilowatt can be written as 1000 watts. Simple. Now, rate of attenuation. Rate of attenuation has been given to us as -2 decibel per kilometer. All right. Now what? Length of total path. Has it been given to us? Total length of 5 kilometer. Length of path has been given to us as 5 kilometers. All right. What next? The power of the signal received is, you just have to tell about the power received. All right. Okay. So since the attenuation is given, the length of the path is given, then I can talk about the loss suffered in the communication channel. So loss suffered in the COM channel will be what? 5 kilometers multiplied -2 decibel kilometer inwards. Kilometer cancelled out. It will be -10 decibel per loss. All right. Now, so the gain term has been given to us as dB 10 log P naught upon Pi. Then, if I want to give it a minus sign, or Pi upon P naught. Simple concept. Then what happens is dB मुझे पता है -10 है. All right. -10 यहाँ पे है, log है, Pi है, P4 है. Cancelled out. All right. Then what am I getting left with? This is equals to 1. Okay, so if this log pi upon p naught is equals to 1, ऐसे होता है ना, then pi upon p naught is equals to 10. All right. Okay, so if I want to find the p naught, it will be equal to pi over 10, and pi was already given to us as a 1 kilowatt signal. So pi has been given to us. Pi is 1,000 watt signal. So in order to find p naught, we just divide it by a value of 10, and then finally we'll be left out with a value of 100 watt as the p naught value. Simple. Now, question 3 we have done, and moving forward to question number 4. So a speed signal of 3 kilohertz is used to modulate a carrier signal of frequency 1 megahertz. Using amplitude modulation, the frequencies of the sidebands will be. Okay. A speed signal of 3 kilohertz is used to modulate a carrier signal of frequency 1 megahertz. Okay. Amplitude modulation, frequency of sideband. Okay. So we'll talk about the concept behind this question first, because this is a mildly like a slightly medium level question, all right? So the process of changing the amplitude of a carrier wave in accordance with the like amplitude of the audio frequency AF signal, all right, that is known as amplitude modulation. First of all, write it down. Amplitude modulation. Actually, what is this? Modulation. So it is the process of changing the amplitude. I'm writing it in the short form. You just get the concept. I'm writing it in the short so that you don't miss it. So it is the process of changing the amp of carrier wave. Okay, in accordance with the amp of audio frequency F. In accordance with the amp of AF, audio frequency. All right, simple. Now, in this A amplitude modulation, frequency of the carrier wave will remain unchanged. Okay, the frequency will not change, but the sideband frequency, what is this sideband frequency? So this amplitude modulation wave, it will consist of 3 frequencies. All right, so I'm writing it over here. Amplitude modulated wave will carry 3 frequencies. Frequency number 1 will be FC. Frequency number 2 will be FC plus FM, and frequency number 3 will be FC minus FM. For this, so these are called the carrier frequencies, and this FC, it is called the carrier frequency, and these are called the sidebands. So in this question, it is asking us to calculate the sideband. The frequency of the sidebands will be what? So okay, and see this already you know now, this will be the greater value, so this is called the upper band, this is called the lower band. This you can logical enough. So sideband frequency, if you want to calculate, we already know the carrier frequency. Okay, it has been given to us. The carrier frequency FC I can write is 1 megahertz. All right, so I can write it as a 1000 kilohertz. Simple. And frequency of speech of signal is 3 kilohertz. All right, frequency of speech is 3 kilohertz. 3 kilohertz. So the frequency of sidebands, what will it be? Megahertz के form में दिया हुआ, I'm so sorry. So FC को you can write it again as 1 megahertz, and this you can write it again as 0.003 megahertz. All right, and तो side वाला हो गया 1 plus 0.003 hertz. I'm sorry, megahertz, comma 1 minus 0.003 megahertz. All right, this will be 1.003 megahertz. This will be 0.997 megahertz. So the correct option is option number A. All right. Moving onwards to question number 5. So, in question number 5, a message signal of frequency WM is superimposed on a carrier wave of frequency WC to get an amplitude modulated wave. The frequency will remain unchanged. It will be the carrier frequency only, but the side bands they will carry a different like see when you change the amplitude of a carrier wave with the what amplitude of the audio frequency you want that is the audio modulation amplitude modulation method, but the frequency of the AM will remain unchanged. So we can say that the frequency of modulator is equal to the frequency of the carrier wave. Now, according to this problem, frequency of carrier wave has been given to us as omega c, and what asking is the frequency of the amplitude modulated wave. So that will be what omega c only. तो यहाँ पे लिखो AM wave frequency is equal to frequency has been we need to find out the frequency. It is equal to omega c then. So it is option number B. So IV characteristics of 4 devices has been shown in figure 15.1. You can see this. Identify devices that can be used for modulation. That can be used for modulation. All right. All right. All right. So basically, the concept behind this question is if you know about a square law modulator, it is a device that can produce modulated waves by the application of the message signal and the carrier waves. You have a carrier wave, you will input a message signal over it, and there's a device that is called the square law modulator, and that will give you the amplitude modulated wave. So this square law modulator that is used for the modulation purpose, its characteristics is shown by the graph formed in the 1 and 2, that is corresponding to linear devices, and by 2 corresponds to square law devices, which shows non-linear relations. Okay. Some part of 4 also follows square law. So option 2, in this question there is no concept, you just know you need to know about this square law modulation device. Okay. And you'll find out that this 2 and 4 they follow the same approximately the same curve that follows this machine requires. All right. So the correct option is 2 and 4. 2 and some regions of 4. C. Option C is correct. Now, hopping on to question number 7. A male voice after modulation transmission sounds like that of a female to the receiver. The problem is due to poor selection of modulation index, bandwidth, poor selection of carrier frequency, loss of energy in the transmission. All right. So a male voice after modulation transmission sounds like a female voice. Female voice. Okay, okay, okay. So that is due to the poor bandwidth selection of amplifiers B. So the concept in this problem is the frequency of modulated signal received. It will become more due to the improper selection of bandwidth. See, male voice, higher frequency. It became a female voice. Oh, I'm so sorry. Lower frequency over here. Like in the male voice, there is more bass, right? So when there is more bass, it is on a lift. It is on a lower lower frequency, and for female voice, the frequency gets increased. They're asking you what did you do? All right. So whatever happens is when you select the poor bandwidth for the amplifier, the frequency will be altered. So this happens because the bandwidth in amplitude modulation that will be equal to maybe the twice the frequency of the modulating signal. So the frequency of male voice, since it is less than that of the female, when you'll do such a thing, it will increase to a higher value, and that will give rise to a more female-like voice. Okay. So, in question number 8, a basic communication system consists of what? It consists of a transmitter, all right, channel, receiver, And information source. No, these two are not there. These two are not there. Transmitter, channel, receiver. These three will be there. Okay. So choose the correct sequence in which these are arranged. And okay. So the correct sequence in which they are arranged in the communication system. So first of all, in the system, what is there? First of all, there is a source. So you can call it info source. All right. Then it moves on to the transmitter. Okay, sorry. Then it moves on to the transmitter. Then it moves on to what? Channel. Okay. Then it moves on to what? Receiver. Then it goes to user of info. Now you can check whichever option is coming first. Info source. So B will be coming first. All right. Then transmitter A. Channel is D. Okay. Channel is D. Then there is receiver is E. And user of info is C. The BADEC. BADEC is option number B. That is the correct option for this. Now, identify the mathematical expression for amplitude modulated wave. Okay. So I'll write it like this. First of all, there is a carrier signal. There was a carrier signal. Carrier signal can be written as AC sine omega C T. All right. Modulating signal. Modulating signal. It is AM sine omega M T. All right. Now, if I want to write the modulated signal, I want to write for the modulated signal. I'll write it as AC plus AM sine omega MT sine omega T. Basically, this is sine omega CT. All right. So this is how you write the amplitude modulated signal wave. Now, if I take this AC common, 1 plus AM upon AC, modulated wave, carrier wave, amplitude sine omega of modulated, whole bar sine omega of carrier T. Alright. Now, you can write it as what? यहाँ पे AC अंदर अगर लेने, then AC plus इसको मैं कह दूंगा mu. Alright. Mu times AC sine omega of modulated sine omega CT. Okay. So mu AC को अब से मैं ले लूंगा K. This can be written as K. So AC plus K sine omega and T sine omega CT. Now what option is matching this? AC plus K2BM T. No. First option is wrong. Second is also wrong. Third option sine omega CT plus 5 and K2. This is K ठीक है. Sine omega MT को उसने लिया है VMT. Velocity depending on time. So option C is correct. उसने sine omega MT को as a function of velocity को as a function of this लिख दिया है. Okay, so option C is correct for this one. Now we have question number 10. So it states an audio signal of 15 kilohertz frequency cannot be transmitted over. An audio signal of 15 kilohertz frequency cannot be transmitted over long distance without modulation because, okay, so they're asking for the reason. Okay, first of all, I'll tell you the concept, then we'll start reading out the options and check for ourselves. So the key concept behind this is that the size of the antenna, like you need to know about the size of the antenna. So for transmitting a signal, we need an antenna, or an antenna is also called an aerial, right? So this antenna should have a size comparable to the wavelength of the signal. I already told you that the length of this antenna should be comparable to lambda. So this is the relation that we mildly use to find the approximate value, or not the exact value. So now for an electromagnetic wave of frequency 20 kilohertz, the wavelength will be what? Wavelength will be 15 kilometers. So such a long antenna will not be possible to be constructed. If the lambda is 15 kilometers, then you'll put 15 divided by 4, so it will be 3.75 approximately. How much will it be? 7.5. 3.75. So 3.75 kilometer long antenna is not practical, right? So we can obtain transmission with a reasonable size of the antenna. So if the transmission is in the megahertz form, then the lambda will be in the hundreds of meters form. And then if that happens, then you can make the antenna comparable to the lambda. So therefore, there is a need of translation so that the information contained in the original low frequency baseband signal that will be converted to a higher or radio frequency. So that the effective if you talk about the power radiated, so power radiated is proportional to the inverse of lambda square, right? Power radiated is inversely proportional to the lambda square. So higher the length of antenna, and higher the lambda, less is the power radiated. So this implies that for the same antenna length, the power radiated increase. The power that is being radiated by the antenna, it will increase as the lambda is getting decreased. So and also, like, the effective power is also in favor of this, and also the length of the antenna is in the favor of this. So coming back to the question, an audio signal of 15 kilohertz frequency cannot be transmitted over long distances without modulation because the size of the required antenna would be at least 5 kilometers, which is not convenient. Absolutely true. The audio signal cannot be transmitted through sky waves. Also true. C option, the size of the required antenna would be at least 20 kilometers, which is not convenient. This is wrong. Too much. They're talking about too much. And option number D, effective power transmitted would be very low if the size of the antenna is less than 5 kilometers. It is also true. So option A, B, and D are true in this. All right. Okay. So next up is question number 11. So audio sine waves of 3 kilohertz frequency are used to amplitude modulate a carrier signal of 1.5 megahertz. Which of the following statements are okay? The sideband frequencies are this and this. The bandwidth required for amplitude modulation is this. The bandwidth for amplitude modulation is this. Sideband frequencies are this and this. Okay, so lower sideband and upper sideband, that is the major focus. So I already told you that is a FC is equals to what? 1.5 megahertz. I can write it as 1500 kilohertz. All right. And the changes in the frequency audio sine wave is 3 kilohertz only. So one will be upper band will be FC plus 3, lower band will be FC minus 3. 1500 plus 3 will be 1503 kilohertz. And the other will be 1497 kilohertz, right? So these two will be the different frequencies. So the bandwidth which will be required will be upper minus lower. So upper is what? 1503, lower is 1497. Difference is of 6 kilohertz. So the bandwidth will be 6 kilohertz, or can be simply written as 2 times 0. Okay, modulated frequency multiplied by 2 is the bandwidth required. Otherwise, I've shown you how to calculate it otherwise. A TV transmission tower has a height of this. Signals broadcast from this tower will be received by LOS communication at a distance of what? Okay. So here height is equals to 240 meters. Distance we do not know. Radius of Earth can be taken as 6.4 into 10 raised to the power of 6 meters. Okay. The maximum distance on Earth from the transmitter to which the signal can be received is what? Root 2 RH. How is it calculated? This is the curvature of Earth. All right. And suppose that the antenna is over here. All right. This is the antenna. The height of this antenna is h. From this point to the center, the radius is r. You want to send the signal up to this point. Let's say this point. All right. Now I'm just so this will be perpendicular. This will also be r. This is the distance t. So r plus h whole square plus r square r plus h. No. Is equals to r square plus d square. So r square plus h square plus 2rh is equals to r square plus d square. For 2 by 2. D square is equals to h square plus 2rh. Now tell me one thing. This height of antenna, is it comparable to the radius of the Earth? One over here, you have the height of antenna ka square. And over here, you have height of antenna multiplied by the radius of Earth. So supposedly this value will be 1 lakh. And this value will be only 1. So we can ignore this. All right. In our calculations, we can ignore this and we can say d square is equals to 2rh and d can be written as under root of 2rh. So this is the distance. This is the distance till which the signal can be transmitted. Although this is not the exact distance because we need to see the distance on the ground like this. But that will be like if you continue you right now, what is important to you is just know this concept of triangle and simply ignore this small value. All right. So since d is equals to under root 2rh, we can just simply put in the values. D is equals to whole under 2 into radius of Earth, 6.4 into 10 is to the power of 6 into h240. So if I need to calculate this, so it is equals to 55.4 into 10 raised to the power of 3 meters. So therefore the range will cover what? 55.4 kilometers. So it will cover what? The options have been given to us as 50, 24 and 55. So B, C, D will be the correct options for this question. All right. Now, next question is question number 13. The frequency response curve for the filter circuit used for production of AM wave should be gain. Okay. So these are the options that have been given to us. So the key concept behind this is again for the sideband frequencies. The AM wave will contain the AM amplitude modulated wave will contain 3 frequencies, namely FC plus FM, which is the upper sideband, and FC minus FM, which is the lower sideband. All right. Now, bandwidth. Bandwidth is the 2 sidebands which lie on either side of the carrier frequency at equal wavelength. So it will be W 2 times WM. This is called a sideband. All right. Now, to produce an amplitude modulated wave, bandwidth is given by the difference between the upper modulated and lower modulated wave, the WC plus WM minus WC minus WM. We already know about this. So the correct options in this case will be 1 followed by 2. 1 followed by 2. Correct. See, upper sideband, then lower sideband. 1 followed by 2. A option is correct. Then 2 followed by 1. It is also correct. It will go on in a like circle. So option B is also correct. C. It is also correct. It is correct. Yeah. So, and this is wrong. So option A, B, C are the correct options for this question. Okay. So next up we have question number 14. So in amplitude modulation, the modulation index m is kept less than or equal to 1 because m greater than 1 will result in interference between carrier frequency and message frequency, resulting into distortion. Greater than 1 will result in overlapping of both sidebands, resulting into loss of info. M greater than 1 will result in change in phase between carrier signal and message signal. M greater than 1 indicates amplitude of message signal greater than amplitude of carrier signal, resulting into distortion. Alright. So the key concept behind this is the modulation index. The ratio of change of amplitude of carrier wave to the amplitude of original carrier wave is called the modulation factor or degree of modulation, MA. Now the modulation index, if I want to write it, modulation index MA equals to amp of message signal. Amp of message signal, it is AM divided by amp of carrier signal. Amp of carrier signal, it is AC. Okay. So when M is greater than 1, for M greater than 1, AM will be greater than AC. Alright. So in this situation, there will be a distortion in the resulting signal of amplitude modulated wave. So the maximum modulation frequency for AM will be delta V max upon VM max, frequency deviation divided by maximum frequency value of modulated wave. But if MF is greater than 1, then delta V max will be greater than VM. Then this will mean that there will be an overlapping of both sidebands of modulated wave, resulting into the loss of info. So in this question, option B, when M is greater than 1, it will result in overlapping of both sidebands, resulting into loss of info. That option is correct. And the next option which will be correct is option number D. M greater than 1 will indicate amplitude of message signal greater than amplitude of carrier signal, resulting into distortion. So B and D option are correct. Next, question number 15. Which of the following would produce analog signals and which would produce digital signals? Okay. Basically, what is an analog and digital signal? These are the gateway of info, or we can say that they are used to transmit information to electric signals. In both these signals, the information, such as an audio or video, is transformed into electric signals. So the difference between analog and digital technology is that in analog technology, information is transmitted into electric pulses of varying amplitude. In digital, translation of information is into binary form. It is either 0 or is it 1, like switching on and off a bulb. That is a digital technology, where each bit is representative of two distinctive amplitudes. So output of a NAND gate and a light pulse produces a digital signal. Like there's a light pulse and there's a output of NAND gate. So C and D will produce a digital signal, and vibrating tuning of musical sound due to a vibrating star string. These will produce analog signals. Basically, what did I tell you? See, analog. It can have a varying amplitude signal. And what about digital? 1 और 0. So 1 और 0 वाले के लिए NAND गेट हो जाएगा. NAND गेट. दूसरा हो जाएगा light pulse. The timing of this 1 and 0 switching will give you the signal. Alright. So this is the difference between the digital and analogs. Okay, so next up we have, would sky waves be suitable for transmission of TV signals of 60 megahertz frequency? So a signal to be transmitted through sky wave must have a frequency range of what? Sky wave के लिए था 1710 kilohertz to 40 megahertz. Alright. But here the frequency of TV signals are 60 megahertz. So this is beyond the required range. Alright. So there is a maximum frequency of electromagnetic wave that is called the critical frequency. So critical frequency. Alright. If your frequency is exceeding this critical frequency, so the waves cannot reflect back. So sky waves will not be suitable for transmission of TV signal of 60 megahertz. Now the important point is sky wave propagation. In it there are the waves which are reflected back to the earth by ionosphere, and in the ionosphere is that is like, I'll show you. This is earth, and this is maybe ionosphere if I'm drawing it correctly. Okay. It is extended above 80 kilometers from Earth's surface and it goes beyond till 300 kilometers. All right. So this is the whole ionosphere I'm talking about. All right. This is the Earth and this is the ionosphere. So what will happen is there is a and a signal goes by through sky waves, gets reflected through the ionosphere, comes back to the surface of the Earth. But if the frequency does not match the required frequency for the sky waves, okay, it is exceeding the critical frequency. As in this case, it is exceeding the critical frequency, then it cannot reflect back. So this frequency is less than critical frequency, but over here a frequency went whose frequency was greater than critical frequency, so it did not reflect back to the surface of the Earth. It just went through the ionosphere. So that is why the critical frequency is important during sky waves concept. All right. Now, next up is question number 17. So, two waves A and B of frequency, 2 megahertz and 3 megahertz respectively, are beamed in the same direction for communication via skywave. All right. Which one of these is likely to travel longer distance in the ionosphere before suffering total internal reflection? All right. So, the refractive index of P layer, the ionosphere layer, can be written as rho equal to A plus B upon lambda C upon lambda 4. So since this is the refractive index, you can write sine I upon sine R, and lambda we already know, lambda mu is equals to C. Alright. The refractive index of wave B is more than the refractive index of wave A because frequency of wave B is more than the wave A. See, frequency of B is greater than frequency of wave A. So the refractive index of B will be greater than refractive index of A. Alright. Sine I divided by sine R is mu. Okay, the lesser the value for R, larger the value of mu. For higher frequency wave, okay, the angle of refraction will be less, bending is less. So wave B travels longer distance in the ionosphere before suffering total internal reflection. Now the important point to note here is that the refractive index of a medium is the characteristic which decides the speed of light in it. Okay, so dependence of refractive index, this is cheese pair. Dependence of refractive index, nature of media, of incidence. All right. Number 2, color of light. Color of light slash wavelength used. Third, temperature of the media. Okay. So the refractive index decreases with the increase in temperature. Alright, now the total internal reflection we talk about, when a ray of light goes from a denser to a rarer medium, it bends away from the normal, and as the angle of incidence in denser medium increases, the angle of refraction in rarer medium also increases. And at a certain angle of refraction, when the refraction of angle becomes 90 degree, this angle will be called the critical angle because now it will rush the so when angle of incidence will exceed this critical angle, then the light ray comes back into the same medium after reflection from the interface. So this phenomena is called the TIR, total internal reflection. Got this concept? Now next is question number 18. So the maximum amplitude of an AM wave is found to be 15 volts, while its minimum amplitude is found to be 3 volts. What is the modulating index? It is a very easy question, right? Modulating index mu can be written as A max minus A min divided by A max plus A min. Alright. Now A is the amplitude of modulated wave, so mu is equals to 15 minus 3 upon 15 plus 3. So it can be written as 12 upon 18, 2 by 3. This is the modulating index. Next up, I have question number 19. Compute the LC product of a tuned amplifier circuit required to generate a carrier wave of 1 megahertz for amplitude modulation. So frequency of a tuned amplifier is equals to 1 upon 2 pi LC. So as per the question is equals to 1 megahertz can be written as 10 is to the power of 6 hertz. 10 is to the power of 6 is equals to 1 upon 2 pi root LC. Now LC will be equal to 1 upon 4 pi square 10 6 square. So 1 upon 4 pi square 2.5. 2.5 into 10 is to the power of minus 14 seconds. Now, next up is question number 20. Why is AM signal likely to be more noisy than a FM signal upon transmission through a channel? Okay, so an AM signal is likely to be more noisy than the FM signal through a channel because in case of the amplitude modulated case, the instantaneous voltage of a carrier wave carried by the modulating wave voltage will be higher. So during the transmission, noise signal can also be added and receiver assumes noise a part of the modulating signal. But in case of FM, okay, the frequency of carrier wave is changed as the change in the instantaneous voltage of modulating wave. So this can be done by mixing and not while the signal transmission in the channel. Noise does not affect FM signal, or simply we can say that noise signals are difficult to filter out in AM reception, whereas FM receivers easily filter out noise. Simple thing you need to remember that in FM, noise can be ignored. Noise can be filtered out. But in AM, noise cannot be filtered out. The receiver thinks that it is the part of the carrier frequency, carrier amplitude. So in AM, it is more difficult. So the frequency modulation MF is inversely proportional to the modulating frequency FM, while in PM it does not vary. We already know all this. So this was the important concept in this. Next up, we have question number 21. The figure shows a communication system. What is the output power when input signal is 1.01 milliwatt? Gain in dB is 10 log 10 P10 P0 by Pt. So distance d of the transmission path is 5 kilometers. Will be loss suffered. Attenuation constant दिया होगा जैसे लास्ट बार को दिया गया था क्वेश्चन में. It is -2 dB per kilometer into 5 kilometers. That will be equal to -10 dB. Okay, so total amplifier gain will be 10 dB plus 20 dB equal to 30 dB. So overgain of signal can be written as 30 dB minus 10 dB, which is equals to 20 dB. Now 20 equal to 10 log 10 P0 by P1. Okay, so log base to 10 P0 upon Pt is equals to 2. So P0 by Pt is equals to 100. Therefore P0 will be equal to what? Pt times 100. So 1.01 milliwatt into 100 will give you XII milliwatt. Okay, so this is where we stop for today, and in the next class I'll do the remaining questions, and also I'll bring up some PYQs or some important concepts which are important for the advanced part. So I'll see you in the next session. Bye bye.